Welcome Math 107 students to the demo for lesson number 24, Zeros of Polynomial Functions. So let's take a look at our first exercise in the demo. When finding zeros of a polynomial function, what kind of numbers can I get? Well, let's take a look at a really long polynomial function in completely factored form where all your factors are linear. Let's quickly review what that means. All factors are linear. That means that the actual power that each of these factors is raised to, each one, is 1. So that's what it means to be linear. Okay, find all the zeros of this polynomial and classify. So we're going to classify them. And the big two categories would be real or non-real. That's first how you classify your zeros. Is it a real number or is it not a real number? And then from there we could be more specific. If it's a real number, is it rational or irrational? If it's non-real, is it complex imaginary or imaginary? So let's take a look at our first factor here, x plus 3. We know that to find a zero, we set the factor equal to 0 and we solve for x. So the first zero is -3, and that's a real number, and it's rational. See the word ratio in there? Rational. It's the ratio of two integers, -3 divided by 1, or multiple ways of writing -3, right? You could say -120 divided by 40 if you wanted. Now what you might notice here is that the factor x plus 3 actually occurs twice. And we still will count this zero, -3, as twice. We'll say that this 0 occurs twice. And if you think about it, you could write x plus 3 quantity squared. It has a multiplicity of 2. So even though it's the same 0, we still count it as two zeros. We count it separately. And sometimes I tell my students, well, you can sort of think of this like identical twins. They're two unique individuals, even though they look the same. And that's what multiplicity of zeros would be. This has a multiplicity of 2 because it appears twice, but you say I have two zeros. They just happen to be the same. Right, my next zero, which is different, is 2x minus 1 equals 0. And when I solve this for x, I get 1/2. So my next zero is 1/2. That's real, and it's also rational. My next zero, x plus the square root of 2 equals 0. When I solve for x, I get the opposite, or negative square root of 2. So negative square root of 2, that's certainly real, but it's an irrational number. My next factor, x take away square root of 2 equals 0. X equals the square root of 2. Square root of 2, rational, irrational. Now my next one looks a little different than what I'm normally used to seeing. This is what we call a complex imaginary zero, 4 plus 5i. So let's see how we would find the zero. Maybe you've already guessed. So to solve for x, I add this thing to both sides, 4 plus 5i. So x equals 4 plus 5i. If you put this right here for x, 4 plus 5i minus 4 plus 5i is definitely 0. So my next zero is 4 plus 5i. That is non-real. And we call that complex. It's a complex number, complex imaginary number. And the reason why we call it a complex imaginary number is, remember, all real numbers can be considered complex as well. Because remember, a complex number has this form, and if b equals 0, then you just have a real number, a. So that's why we have to call it complex imaginary. We can't just say complex number because -3 and 1/2 can also be written in that form. All right. The final one, you may have guessed, is 4 take away 5i. So that's non-real. And it's also a complex imaginary number. Ooh, my pen just went crazy on me. Complex imaginary number. All right. What degree does this polynomial have? Well, we can't just look for the highest exponent like we might normally do because it's not in polynomial form. Remember, polynomial form is a finite sum of terms. So we don't have a bunch of addition and subtraction going on here between, it's not written out as a sum. It is written out as a product. It's a product of all these factors. So in order to find the degree, you have to add each of the exponents on your factor. So you have 7 ones, so the degree is 7. You have 7 linear factors. And how many zeros? And this is the only tricky part. How many zeros does it have? Remember, counting repeated zeros separately. So that's the twins here, the identical twins. So -3 occurs twice, so you count that as 2 zeros. And then you've got these other 5 zeros here. So you've got 7 zeros. Right? So that's sort of an introduction to all the different types of zeros you can have. Later on, we're going to be doing quite a bit of sort of algebra multiplication with using some of these complex imaginary zeros. So I wanted to just give you a little strategy for multiplying. Oops, hang on, my pen just came out, so I've got to shut this off. Okay, I'm back. The first thing I want to do, I'm just going to open up a new page here, is I just want to review something with you. If you had two factors that look like this, do you remember that when you see two factors that looks like this, that your middle term and your outer term are opposite, so they just become 0. And what you end up with is your first term in each one, x, is squared. Your second term is 2, that gets squared. And because your operations here are addition and subtraction, you get minus. So this is often referred to as the difference, because of that subtraction, between two squares. So the difference between two squares can always be factored into factors that look like this, where they look almost the same except for one is addition and one is subtraction. And to get what goes in each factor, you take the square root of your first term. Square root of x squared is x, at least assuming x is positive here. And then the square root of 4 is 2, and you put plus or minus. Okay, so then if you recall earlier, we talked about multiplying numbers that are factors that had I as part of them. So for example, x plus I, x minus I. So again, our middle and our outer term, when we add them, go to 0. And we square I, and we square x, and we put a subtraction between them. However, when we simplify this, don't forget I square is -1, because I is defined to be the square root of -1. So when we complete this, we get x squared take away -1, which is x squared plus 1. So now you have the ability to factor the sum of perfect squares. We couldn't do it with real numbers, but now that we have these imaginary numbers, we can do it. So what do we do now when we have something like this? Well, your first inclination would be to say x times x and then x times that, and do the whole distributive property, and it could get pretty complicated. So I want to show you just a little kind of sleight of hand that's legitimate, and it makes life really easy. Let's come back here. So all I'm going to do here is I'm going to rewrite each one of these factors by just distributing the negative sign. So x minus 4 minus 5i, and keeping each factor as 3 terms initially. X, take away 4, take away 5i, 3 terms. So my next factor will be x minus 4 plus 5i. Okay. Now here's a nice little sort of strategy you can use. Instead of grouping the 4 and the 5i together, group the x minus 4 like this. Now try to look at this by seeing this purple x minus 4 here as just one number. So like think of this as big capital X minus 5i, big capital X plus 5i. Do you see that it looks like these factors? They look the same except for one is addition and one is subtraction. So these two factors are conjugates of each other, which means when you multiply this with the distributive property, the middle term and the outer term are opposites and give you 0. So all you have to do is take your first term, which is x minus 4, and square it. And then remember your operation is subtract. It's always the difference. And then you square your 5i. And now it's just a little bit of algebra. X minus 4 times x minus 4 is x squared minus 8x plus 16. Takeaway, 5 gets squared and I gets squared. 25i squared. But remember now that I squared is a -1. So this becomes x squared minus 8x plus 16 plus 25. Okay. So our final polynomial here would be x squared minus 8x plus 41. So we combine these two terms. So you will be needing to practice this, and I would suggest that you shut off the video now and you try this again on your own once or twice to make sure you have these steps down, because you'll be doing this in your class activities. So let's take a look at problem number 2. Problem number 2 says consider the function 2x cubed plus 2x squared minus 10x minus 4. So this is in polynomial form, right? It's a finite sum. We're going to find the exact values of all zeros of this polynomial and then write it in completely factored form, where a is your leading coefficient, and every single linear factor will always have this form. X take away your first 0, we'll call it C1. X take away your second 0, we'll call it C2. And X take away your third 0, C3. Now notice the degree of my polynomial here is a 3. So that's why I have 3 linear factors written here. Now you might ask, why do you have C1, C2, and C3? Because all of your zeros are complex, whether they're real or complex imaginary. So that's my guess anyway as to why it's C1, C2, and C3. So one thing you can always do when you look at a polynomial is you could put it into your graphing calculator to find, hopefully, an integer value 0, so that you could start to find your remaining zeros through long division. So if you use your calculator, you get a screenshot like this, and if you use Geogebra, you get a screenshot like this. And what you notice here is that you have 1 0 that you can quickly pick out x equals 2. Okay. Before we start, I just want to show you something. This polynomial, and this is something you could sort of miss doing, this polynomial, when you look across at each single term here, you see that it has a common factor of 2. So if you pull the 2 out as a common factor, notice your remaining polynomial, your remaining factor here is x cubed plus x squared minus 5x minus 2. So I want to show you something with GeoGebra. So right now, I have graphed in GeoGebra the same thing that you see on your paper. This is the function 2x cubed plus 2x squared minus 10x minus 2. Notice I now have the function x cubed plus x squared minus 5x minus 2, which is the same as this one, but each term here is divided by 2. You see that the function on your paper is just a vertical stretch by a factor of 2 of the blue function. Notice the zeros are identical. So when you happen to see a polynomial, do I want to save it? No. When you see a polynomial written in this form, you always want to check to see if there's a common factor. And then you pull that common factor out, and then this will be the polynomial that you want to try to factor completely into 3 linear factors. See, I know it's 3 because of the x cubed here. All right, so the first thing I do is I pull out the common factor. I know x equals 2 is a factor of this. And if x equals 2 is a 0, so if x equals 2 is a 0, I was jumping ahead, did you notice? Then I know x minus 2 is a factor. Because if I put a 2 in there, I get a 0. So that means the first thing I can do here is if I know a 0, I know a factor. That's the wonderful thing about zeros and factors. You get 2 for the price of 1. So what can we fill out right now? We can call a 2, and we can call our first factor x minus 2. So we are going to have a factor left, and it's going to be some kind of quadratic factor. Okay, quadratic because this is 3 and this is 1. So I know that whatever's inside this second parentheses has to have an x squared in it. Now the next part is really important, and I'd like you to read it. Your homework, and this should say, your homework on lesson 24 says to use the rational zero theorem, Descartes' rules of signs, and possibly the graph shown by the graphing utility as an aid in obtaining the first zero. You can ignore the parts of the homework directions that says to use the rational zero theorem and Descartes' rule of signs. You should just take your polynomial that's given, either put it into a graphing calculator. If you do not have one, then use Geogebra or some other free graphing software that you may know of. Desmos is another one, to find your very first zero. Once you find that first zero, then use long division to find your remaining polynomial. So that's what we're about to do right now. We know our first zero is x minus 2. Okay, so we are going to find, let me take the 1 off of here, x minus 2. So we are going to divide x cubed plus x squared minus 5x minus 2 by x minus 2 to get this quadratic factor. So let's do that. We're going to use long division. So we have x minus 2, and we're going to divide that into x cubed plus x squared minus 5x minus 2. So we start our process. X goes into x cubed, x squared times, and I write it right above my square term. And then I multiply x squared times x minus 2, and I get x cubed minus 2x squared. And now I have to remember to change the sign when I subtract, so that becomes a minus and that becomes a plus. And now that goes to 0, and I get 3x squared. I bring down my next term, minus 5x. And now I say, how many times does x go into 3x squared? My answer is plus 3x. And now I take 3x and multiply it by x. I get 3x squared. I take 3x and I multiply it by negative 2, and I get negative 6x. And when I subtract that, I have to change signs on both of these, and now I get 1x minus 2. And isn't that beautiful? Because it matches the divisor. So x minus 2 goes into x minus 2 one time, x minus 2, and when I subtract that, I get 0. So now I know two of the factors. I have factored this cubic, right? This cubic right here, this cubic polynomial, into these two factors. So now I can write f of x as 2 times x minus 2 times this quadratic trinomial right here. I call this a quadratic trinomial because it has degree 2, and that's what quadratics have as a degree. And there's 3 terms, so it's a quadratic trinomial. All right, so remember our original goal was to find all the zeros of the function. So we're going to set the function, now written as a product of factors, equal to 0 and solve for x. So here's my function. 2 is never going to equal 0, so I don't have to worry about that. And I set each factor equal to 0. X minus 2 is 0. Then I get a 0 at 2. But we already knew that from the graph, right? We knew this. We got this 0 from the graph. Got 0 from the graph. Okay. So if we look at our graph back here, it looks like we have a 0 just to the left of 0, so some kind of small negative number. And then it looks like the other zeros a negative number between negative 3 and negative 4, and closer to negative 4 than it is negative 3. So that way we get some indication when we find our zeros if we're in the ballpark or not. So we've used that factor to find the first 0. So now we have to use x squared plus 3x plus 1 is 0. And in order to solve this, we have to use our quadratic formula. So we get 3 squared minus 4ac all over 2a. X equals negative 3 plus or minus the square root of 5 over 2. So here's our zeros. We have a negative 3 minus the square root of 5 over 2. We have a negative 3 plus the square root of 5 over 2. And then our largest zero, the one furthest to the right, is a 2. So these are the exact zeros, exact. If you wanted to estimate them so that you could, you know, put a little dot on the x-axis here for your x-intercept, then you could estimate these to 1 or 2 places. So let's just make sure we're in the ballpark based on what our graph told us. So let's just see what negative 3 plus the square root of 5 looks like, all divided by 2. Negative 0.38, so that was the x-intercept really close to 0. And let's take a look at negative 3 minus the square root of 5 divided by 2. Did I look at that wrong? I thought it was between 3 and 4. Let's see, negative 3 plus the square root of 5 minus the square root of 5 over 2. Let me try that again. Negative 3 take away the square root of 5 equals divided by 2. Same answer, negative 2.6. So let's see, I'm going to come up here. Maybe I didn't look at it correctly. Oh yeah, that's negative 1, negative 2, and that's negative 3. So the zero's approximately negative 2.6. All right, So the exact solutions, here's your smallest solution, your next smallest, and then your largest. So since you're solving for x, your answer is a solution set. So if you have to write this in my math lab, this would be the order that you write your solutions in. Okay, so it says now that we have finished finding the zeros in part E, let's use all three zeros to write this polynomial in completely factored form. So our zeros are -3 minus the square root of 5 over 2. I'm going to put that all in parentheses. -3 plus the square root of 5 all over 2, and the number 2. So my leading coefficient was 2. That was the greatest common factor in this case. So my first factor is x. Take away one of my zeros is -3 minus the square root of 5 over 2. My next zero is x take away -3 plus the square root of 5 over 2. And then finally x minus 2. What's the degree of the polynomial? It's 3. How many linear factors do we have? We have 1, 2, 3 linear factors and 3 zeros. So all of this can be summarized in this following box. And this now is something you want to take a little time to read and try to digest. So here are the conclusions about polynomial functions. If a polynomial function is of degree n, then counting multiple roots separately, the equation has exactly n complex zeros. That's real and non-real. Now, if you recall, when we first started talking about polynomial functions, we said at most n real zeros. We had to use at most because we were only talking about real zeros. But now that we can talk about these complex imaginary zeros, we can now say it will always have exactly the same number of zeros as the degree of the polynomial. And that's really cool. An nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors. So you always will have the same number of linear factors as the degree, and each linear factor will always have the form of x take away your zero. Whatever your zero is, it could be as simple as the number 1, or it can be as complicated as one of the ones we just looked at, -3 plus the square root of 5 over 2. Okay, but it will always have that form, x take away your zero. Now, if your zero happens to be a negative number, it's going to be x take away a negative number, which simplifies to x plus the number. Okay? So here's a nice little thing to notice. If you have a zero of this form, it's a complex imaginary zero. If a plus bi is a zero of your function, where b is not equal to 0, then your imaginary number a minus bi, its conjugate, is also a 0. That is, imaginary roots, if they exist, always occur in conjugate pairs. Always. So irrational zeros also occur in conjugate pairs. So if you see 1 plus the square root of 2, you're also going to see 1 minus the square root of 2. And you should be fairly familiar with that idea, because let's suppose you're solving a quadratic equation. If you got x plus the square root of 2 for an answer, you would also get x minus this plus or minus the square root of 2. You always get 2 zeros out with the quadratic equation. So if you have an irrational zero in this form, you always have a conjugate pair. Same with your complex imaginary. Well, actually, you could just have like square root of 2 here, and then you would have the opposite of that, negative square root of 2. All right, so here's the type of questions that you're now going to be asked, and you have enough knowledge with a little bit of practice to answer these. Find a third degree polynomial function, f of x, with real coefficients that has -3 and I as zeros, and such that if you put 1 into your function, your output is 8. Give your answer in both factored form and standard polynomial form. Woo, that's a lot to digest. So let's take it one step at a time. The first thing that I do is when I see that I have a third degree polynomial, I just start a very general form of the polynomial where I have some leading coefficient that I don't know the answer for yet. And since it's a third degree, I'm going to write 3 groups of parentheses. I'm going to have 3 linear factors, and each factor is going to have this form: x take away my first 0, x take away my second 0, and x take away my third 0. Again, noticing that the power on each of those zeros is 1, and 1 plus 1 plus 1 adds up to 3. So that's the very first thing that I do. Then I look at the next bit of information that has -3 as a 0. Well, if -3 is a 0, if I add 3 to both sides, see, when x is -3, then x plus 3 was the factor. So now I can do this. If -3 was a 0, then x plus 3 was the factor. Okay. What else can I use from that sentence above? It also tells me that I is a 0. But you might say, geez, I need 3 zeros. I don't have enough information. But guess what? I is an imaginary number, so it is going to have a partner, -I. So even though we don't tell you that you have -3 and plus and minus I as zeros, you have to remember that any complex imaginary, or in this case just an imaginary number, will always have a partner. So you can fill this in by saying -3 and plus or minus I. There's your third 0. So now you can come up here and you can say, okay, I've got x take away I and x take away a -I. And x take away a -I is going to simplify to be just x plus I. Wow, you might think you should be totally done by now. You've done all that work. You've used all the information we've given you. However, we have to figure out what the leading coefficient is. And you have done this over and over, whether it's been for a straight line or when we were looking at quadratic functions where we had the vertex form and you had to find the coefficient. The only way you can find A is if a little birdie comes along. Let's write f of x as y because this is a little helpful for you to see. If a little birdie comes along and it tells you the coordinates of a point that lies on the graph of this function are the coordinates of a point that's a solution. So do we know an x value and its partner y that satisfies this function is a solution for the function or is actually a point on the graph? We don't see the graph, but we see something right here. F of 1 equals 8. 1 is our input value, our x, and f of 1 is the same as our y value. So to find A, I substitute 8 where I see y, and where I see x, I'm going to substitute a 1. And then I try to simplify this as much as I can. And now you say, what do I do now? Well, you know how to multiply this. 1 minus I, 1 plus I. These are conjugates, so you square your first term, you square your second term, you put a minus there, and you get 1. Oh, anytime I get too close there, my pen goes a little crazy, so let me just undo that. Control Z should undo it. There we go. So this equals 1 minus, and remember, I squared was -1, so this becomes 1 plus 1, which is 2. So when I multiply these two factors, I get a 2. So 8 equals 8a. A is 1. You mean I did all that work just to get a is 1? Oh well. So here's your final function. F of x equals 1 times x plus 3, x minus I, and x plus I. That's your final answer. That's your polynomial function in completely factored form. Okay, that should be enough for you to think about before taking on your class activities. And make sure you save a lot of time for your class activities. There's a lot of polynomial multiplication involved in those activities. So you want to make sure you have a lot of scrap paper around. And I will do that video for you shortly. So if you have any questions on this demo, please feel free to email me. I will be glad to help you out with any questions you have.